Good evening, everybody. With this talk, I want to share our small experience we had at Intecs about 802.11p. In case you don't know Intecs, I know for sure this. We are a medium-sized Italian company. We work on software for real-time embedded systems. So, I don't know if you've ever heard of intelligent transportation systems. In case you don't, I can give you a very, very short presentation. An intelligent transportation system is a set of devices and network equipments that help transportations. It can help transportation in many different manners by giving the drivers indications on whether they should follow another direction than that intended, maybe because of a road accident or because of traffic jams or because of any other reason. It can also collect pay tolls and can do a lot of very nice applications. They are still figuring out what an intelligent transportation system can actually do. What we know is that such a system, regardless of what it actually does for making money to the people who own it, is made of basically, this is a laser pointer, yeah, of cars and of devices which are located close to the road. These devices are called typically roadside units. So we have units that are installed on board of the cars, they are called onboard units, and roadside units. And they have to talk to each other for knowing whether there has been an accident or how many cars are passing by in a road. The problem is, there is no easy solution, no easy technical solution, in this case, for having cars talk with these roadside units. If you are a telco operator, I don't know, are there any telco operators in the room? Okay. If you are a telco operator, but you are not, then you would just say to me, okay, you can use LTE or UMTS or whatever technology we already have, and we can deploy for you if you want. The problem with this is that it would require that every car has a SIM card and has a contract. So the tech operator would be very willing to have the users pay for those SIMs and contracts, but the user will not pay. This is a fact, at least for now. Research studies have shown that the user will not pay €5 per month, which is the cost that the operators would like to have for having this kind of life-saving devices on board. It might not be true for you, but it is true for most people in Europe and also in the US, where these studies have been done. So this is not viable. Other solutions based on non-cellular technologies can be done. For instance, you might use Wi-Fi 802.11. It works in this room, it works in the airports, it works in the stations. The problem is, where we have cars, usually it is an outdoor space, and you don't have many access points there. So you don't like Wi-Fi 2. They had to invent a new technology for that. Both the IEEE and the ETSI, which is the European Institute for Telecommunications, have decided that a new architecture for the networking for this spatial environment was needed. They have done some efforts, and basically there are two main problems. The first one is that you need a communication system that allows you to send messages not in a host-to-host manner like you do in the internet, when you have your computer and you want to talk to Google or to YouTube, but in a geographical manner. Because in many cases, you don't know, the road operator does not know to which car it wants to send a message, but it knows for sure that it wants to send a message to any car that is in a given location, because there has been an accident. This is totally different from how the internet works. So they need modifications to the networking layer and also the upper layers. The second problem is that from a wireless point of view, of course you need wireless. I didn't mention the wired alternative, but I don't think we need to. Okay, so as in a wireless environment, this is a very harsh environment because in the city you have many buildings and the wireless waves do not like buildings. They are not able to go through at the frequency you want to use there. If you are far from the city, if you are in a suburban area, there you don't have buildings, but you don't have cars. So it is also, or you have not so many cars, so it is difficult to find other cars for communicating with. If you go on a highway, you have many cars, you don't have buildings, but the cars move very fast. And that's another problem with wireless waves, because when they move very fast, they change, as you know. So they have to develop, in addition to network layer and above for the addressing routing stuff, they also had to invent a new technology for the lower layers, for physical layer and the medium access control layer. They did so at the IEEE by modifying the 802.11. This is of course for practical reasons, because it's a very well-known and widely deployed standard, so you already have mass volume of production for that. And I did a few modifications to the standard. They called the amendment 802.11p. It has been released in 2010. Most of the modifications are at the physical layer. Some modification is at the MAC layer. Now we will very fast go through the main modifications. I'm assuming that you know at least a bit of 802.11. If you don't, I'm afraid you will miss something. In case, I apologize. Regarding the MAC layer, the biggest modification they did is to remove the need for associating to an access point. So when you are in this room, you want to connect your laptop or your smartphone, you have to choose which network to connect to. You have to somebody to tell you the name of the network, because the network might not even be telling you that it is there. With cars which move fast, this is impossible, because it would take too long for a car to understand that it is in range of an access point, and then it is already gone, especially in a highway, for instance. So instead of doing this, they decided to use a special name of the network, a name that is made of all ones, as is always the case for special names. And it is called a wildcard basic service set. So cars do not connect to any access point in particular. They always are connected by default to this special network. They don't need to associate. Additionally, at the MAC layer, they have defined a modified table for these very funny numbers there, but it's not very important actually. Let me go to the physical layer instead. At the physical layer, 802.11p has been reserved a frequency band that can be used only for this purpose, so there is no risk of collision with the nearby Wi-Fi for while downloading movies or doing any other thing, and not even with other technologies. So they allocated a reserved spectrum for that, both in Europe and in the US. It is on 5.9 gigahertz. It's pretty high. They decided to use the orthogonal frequency division multiplexing, which is very popular. It is used by 802.11a, G, and all the newest releases of 802.11. But they used it at 10 megahertz with a double OFDM symbol duration. If you know what I'm talking about, this means that it is more robust. So both inter-symbol interference and the Doppler spread. Doppler spread is what happens when the cars move fast. So this is something that you can also do for typical Wi-Fi, but you would waste a lot of bandwidth. You don't want to waste bandwidth for commercial typical uses, because usually you are either static or you don't move too fast. With cars, you allow to waste a lot of bandwidth because you need this kind of robustness. For similar reasons, they increased the maximum transmit power. So in a regular 802.11a or G, the maximum power is 200 milliwatt, and while in 802.11p it can be up to 2 watts. So it's a tenfold increase in the maximum power. And this is because 802.11p will not be used in indoor environments where people usually live, so it should not harm too much. As you know, that they don't know actually if wireless waves harm people, brains, and stuff. But there is the approach of having as little power as possible. In this case, the as little as possible is 2 watts. Furthermore, they decided to have a more skewed spectrum emission mask. This can be seen with this graph. The thick gray line is what you are allowed to do with the regular Wi-Fi. So if this is the catered frequency, you can have here the full transmit power. When you move like 5 megahertz or 10 megahertz bandwidth from the frequency center, then you have to drop your power, and then you have to drop it even more when you are further away. In the case of 802.11p, for all the transmit power classes, there are 4 classes depending on the type of devices, you have to be more stringent. So you can use maximum power when you are close to where you want to transmit, but as soon as you go far from that, so this is an area of the spectrum where in principle you should not transmit at all, but you will transmit because the transceiver is not perfect, it's not an ideal transmitter, but you have to use more costly and more sophisticated filters for dropping the power. So you are allowed to use more power, but you have to use that power in a wise manner. You cannot just use that power for interfering with all the other channels and harm brains of people. We started working at Intecs with 802.11p in a regional funded project, a project that has been funded by the Tuscany region, where we are based. And we had so little time, it was a very short project, 18 months from the beginning to the end, by having to provide a full end-to-end system with a demonstrator. So we couldn't really waste our time to think how things worked. So we just meshed up the system, made the demonstration, and we were done. After the project finished, we decided to go back our steps and try to understand exactly what we have done. What we had done is using these cards. These cards are the prototype cards with 802.11p, which are manufactured by NEC, but are not for commercial use. They have been developed in the context of European projects, past European projects. They are widely used for research, but they are not sold. They cannot be installed in cars. We wanted to we wanted to do some serious measurements using these cards and provide the results to the community. Actually, after the very first steps, when we did the first cross-check experiments for verifying that our scripts were working, we found out that the cards were not working as expected. So we had to stop and change the subject of our investigation. So instead of doing measurements, we had to research on why the cards could not be used as for measurement themselves. So we did now in this paper and in the slides I will just describe a very simple experiment, but which can show you what are the limits of these cards. I don't want to be, I'm not against these cards. I mean, they're not sold, so I'm not against NEC or whatever. I just want to point out what we had to do just to verify what can be used and what cannot be used for testing. Since this is a sort of significant for, this is sort of something that can tell you how mature is the technology. We did a very simple experiment with a transmitter, one card, another card, a receiver. And we cross-checked our results by doing this with different technologies, so in addition to 802.11p, also 802.11g, and also by, without having the air in between. So we also connected the two cards with a cable, just to verify that we didn't have much noise in our lab. What we found out is that this curve here is what you should be able to achieve if you had a good cards. Here, theoretical, maybe it's not the right word now that I think about this, because it's not theoretical in the sense that raw throughput or something that you can never achieve. You can achieve this, you should achieve this. When we run the experiments with 802.11a Atheros card, which cost €5, we achieved the full performance. It's just something that you cannot achieve if you have more than one transmitter because of collisions. However, in the case of 802.11p, we didn't achieve, and the difference was quite remarkable. So we spent a lot of time wondering why it could be this, and we tried to remove all inaccuracies, starting from our developing errors of when we wrote the scripts and the test measurements. But actually, we found out that the problem is in a combination of the chipset and the kernel driver. We cannot be sure exactly where is the inefficiency because we don't have the source of the kernel driver, because in this case it is not an open source driver, but it is provided in a binary form. I want to mention here that it's not a problem of the card of the processing unit itself, because if we instead of 802.11p we connect the two cards with an Ethernet cable, then the processor is fast enough to achieve full bandwidth. So to summarize, yes, 802.11p is a reality. It has been released 1.5 years from now. There are products coming out, but we are not yet there. So if you think about 802.11, plain 802.11, the huge mass volume that I have achieved, we are very far from that. And this is also true for the newest standard. So if you take 802.11n cards, they were out before the standard was even approved. And even at that point, they were good enough for production. This is not the case for 802.11p, and my personal opinion is that this might be due to the fact that at the moment not everybody is, they didn't find so far a credible business model for actually selling these devices. The problem is that it is much easier to put on the market 802.11 cards because you put them into computers. And computers have an expected lifetime of 2 to 5 years, 5 in the very, very lucky cases. For cars last much longer. So it is very difficult for anybody to have a credible business model that takes into account that you will have for 20, 30 years most cars without this kind of equipment, and you will also only increase them in a very incremental manner. So for the same reasons, manufacturers are not rushing to go onto production volumes for this kind of chipsets. But of course they are good for experimenting. So if you want to do your research experiment, a lot of research experiments have been done with these cards that works. There are also others that have been that are sold by other companies like Denson or Venice. Another option that you might want to evaluate if you want to do research on this topic is to use software-defined radio, because in the literature there are some researchers have shown that you can do with a USRP or other radio frequency front ends and a laptop, you can emulate fast enough 802.11p, at least in the encoding part. I guess it can be done also in the receiving part. So if this is, in that case, you might be able to control every single bit you want to encode, modulate, transmit. So for experimentation, that's another good option instead of going for black box commercial device. And this concludes my talk.